Okay, I'm Steve Shaw, and I'm going to be talking about HammerDB, a better way to benchmark your open source database. So as said, I'm Steve Shaw. I work in open source databases at Intel, and I'm also the main developer of HammerDB. So what is HammerDB? Well, firstly, it's not a database. So given the naming, I mean, the name HammerDB actually comes from the application started off supporting Oracle. So it was a tool called HammerOra. And since we moved to, supporting a much larger number of databases, that name was no longer appropriate. So the most suitable name was called HammerDB. So what it is, it's the leading open source tool for benchmarking relational databases. So the focus is very much on relational databases because they tend to be the databases that give you the best performance for sort of this approach in terms of benchmarking. It supports, say, the interfaces of, so we have a GUI interface, as you can see there. It also has a command line, which runs in both an interactive and scripted mode. And there's also a web REST JSON-based interface. It supports industry standard benchmarks, and it has high performance and scalability, which is built into the design, which is something that we'll talk about as we go through the presentation. So it's, as mentioned, it's open source. It's hosted on GitHub by the TPC Council since 2019. So they're the industry standard body for database benchmarks. So it's a good home for the application. There's a TPC OSS subcommittee, which oversees and approves all of the changes for HammerDB. So it's open, and also there's a large amount of input in terms of what goes into the benchmarks. All of the source code is available. It's GPL3, so it's all available on GitHub, and there's binary releases as well. So if you go either straight to GitHub or if you go to HammerDB directly on the download link, then you can download the binary releases there. And it supports both Linux and Windows natively on 64-bit. So you have the defaults, you can use both the GUI, so you do have a GUI for both Linux and Windows and command line, and exactly the same look and feel, regardless of which operating system that you're running it on. Importantly, though, it supports Linux and Windows on x86 64, but you can test databases on any platform. So if you run HammerDB on your x86 system, then you can connect via your database interface to a database running on any particular platform that you choose to test. Also, if you have a look on, say, the HammerDB website, there's a link there which shows you the release downloads and the popularity between the different versions that are released. So the databases that HammerDB supports, there's no surprising. I'm sure many of you are familiar with the DB Engine's website. So it'll be no surprise that HammerDB supports the most popular relational databases, so both commercial and open source. So I said it started off supporting Oracle, but it supports Oracle, SQL Server, DB2 on the commercial side, but also there's a key focus there on open source. So clearly the goal is to be able to support the most popular databases out there. And also, a crucial fact is to be able to provide comparisons between different database engines. So we don't want just an application testing one particular database. We want metrics that be able to give us the comparison between how those different database engines work. So there are other databases supported, but the key focus is very much on those top relational databases to ensure the widest use. For the workloads, we've mentioned that they're TPC, and they have standard benchmarks, both in the transactional area and in the analytic area. So the name of the workloads within HammerDB are TPC-C and TPC-H. So TPC-C for transactional or OLTP, and TPC-H for OLAP or analytic type workloads. It's fair to say probably the most popular, and if you're just starting out, probably the one where you'll be able to ramp up most quickly is in terms of the OLTP and transactional workloads. This has been derived from the TPC Council specification TPC-C, and if you go to the TPC website, you can see a large number of the fully approved and audited benchmarks that have been done with the TPC-C specification, and similarly with TPC-H. Now, it's important to point out that within these supported workloads, the key word really on this slide is derived. So these workloads are derived from TPC-C and TPC-H, but they're not full TPC-C and TPC-H benchmarks. We'll talk about cached and scaled benchmarks later, but it's important just to draw that distinction between them being full workloads and fully audited, and the approach where you can take these sort of benchmark specifications, take the essence of them, and run them very much within your own environment. Finally, as well, it's worth noting that you're not permitted to use TPC-C or TPC-H for derived workloads, as this is in fact a trademark violation. So that's why HammerDB has TPC-C and TPC-H to very much draw out this distinction. So some key database benchmarking concepts. So what is the approach that we want to take in running a database benchmark? And why is HammerDB a better way to run these benchmarks by design? Well, the key thing is our databases are designed to manage concurrency. So the concurrency control should be in the database and not in the client. You want the database receiving multiple sessions, all trying to access the same data at the same time, and see how our database can actually manage that side of the workload. So we have this locking and latching inside the database, and that should be a crucial part of the test that we run. So what we don't want is the concurrency control inside the client compared to what we're running across the database. And doing that way, this is the way we can sort of validate the difference between how different databases, both commercial and open source, handle this concurrency overall in the workloads. An important thing to point out as well is that because HammerDB supports these commercial databases as well as open source, if we take an example now, you should accept to see on a 2-socket server about 6 to 7 million new orders per minute, and we'll define that later on. So we've got high confidence levels that HammerDB can drive the database to almost full CPU utilization and see very high throughput on the client side. So that means if we're not doing that when we're testing a database and we're not using all the CPU to full utilization, then the bottlenecks are in the database, and that helps us drill down on where maybe scalability gains could be made on the database side. So what languages do we use for database benchmarking? So, and especially when we're designing for this high performance and scalability. Well, it wouldn't be too surprising that you would test your database in SQL or SQL, and that's exactly what HammerDB does. So it has the database commands in SQL. It also has the application logic in stored procedures, and right at the lowest level we have the database interfaces in C. Now, when we're running this, so we've got very, low-level, high-performance database interfaces, and we can see in comparison, to the language, it's actually all compiled up in bytecode, so it has much higher levels of performance than the application logic actually built into the databases. But the reason we're using stored procedures and focusing on stored procedures is we're spending more time in the database. So we're essentially making one call to the database, and then letting the database do all the work, rather than spending all our time in the round trip time. This is crucially important because as CPUs get a lot faster and we get a lot more cores, the time that it's spending processing those commands in the database is getting smaller and smaller over time. So that means proportionally we're spending more time, if we're not using stored procedures in the round trip time, than we are actually in terms of running, the full database workload and testing that concurrency that we mentioned earlier. So what this means is we've got more resources to actually drive the workload rather than in the benchmark client. And if we look at a comparison between different approaches, and you can run this sort of test yourself, we can see at the system level utilization, in HammerDB, it's around about 3%. Comparison we did compared to, for example, Sysbench, which is not using stored procedures but doing this round trip, is then spending about 20% of the time in the socket type network layer. So we've got the interfaces in C, we've got the stored procedures, we've got the SQL interface. Now we need a language to glue this all together, and this was one of the key concepts, and quite often a regular question of using the best language for the job that we need to, the best language for the job that we need to do, particularly at time. So if we have a look at an example here, that as part of the design process, we looked at using Python as this glue language. And clearly, right from the outset, one of the big challenges with Python is called the GIL, which limits Python effectively to single threading. So it can run multiple threads, but it can actually only run one thread at any one point in time. And as we've seen from the previous slides, we want to actually test the concurrency on the database. So what we don't want is concurrency being managed in the client. And that's exactly what you would get if you were trying to run a database benchmark in Python. We want to see full scalability, and a high performance. So the only language that provided those sort of capabilities was called TCL or TCL. So that's exactly what we use, in HammerDB for that multi-threading. So all of the virtual users are essentially an operating system thread. They all load their interpreter, as we mentioned before, that compiles into bytecode, for high performance, and they can run independently across a wide number of CPU cores, which gives us this high level of scalability. We use coroutines, but only when we're running event-driven scaling, as we'll mention later on. Also, this using TCL provides us both the GUI and command line on exactly the same code base. And finally, almost the icing on the cake, if you like, is the TK GUI that is available in Python as well, is native to TCL. So it supports, for example, 4K UHD scaling, and we can use this directly in TCL as well. So we can have an advanced GUI at the same time as using the CLR command line, but also have everything running high performance in multiple threads. So one of the key concepts, as part of this sort of introduction side, one of the key concepts, and arguably one of the most misunderstood areas, is this concept of cached versus scaled benchmarks. So if you're setting out, or you're not sure, you're not fully expert in terms of database workloads, right at the top level, I would say the default mode is cached workload. That's what you should be using to be able to minimize the overhead, the cost in terms of setting up systems, and being able to get the best and most consistent, performance results. The difference is that with a cached workload, the GUI restricts you to building 5,000 warehouses. Not that there's any restriction in the code, it's more a nudge in the right direction, so you're not trying to overbuild the schema, which is a common error that we see. Typically for a cached workload, what we're aiming is to have all of the data from the data disk cached into our database buffer cache. So we're going to see minimal activity to the data disk. Instead, we're aiming to make the workload CPU and memory intensive, so it's going to be very high performance. And on the I/O side, what we will see, and where we're looking to get high performance as well, is a stream of writes to the WAL or the redo disk. So on the logging side, that's where we're going to see most of the I/O activity. After a ramp-up period for this cached workload, most of the data will have been read from the data disk and then reside in memory. So we're not going to see as many writes, unless we're actually deliberately, causing checkpoints as part of our design. During a normal workload, we wouldn't necessarily see as many writes back to that data disk. When we're doing a scaled workload, now this is simulating more of what we would see typically from a fully audited TPC-C type workload, where we have a lot more than 5,000 warehouses. So we're going to scale the workload in proportion to the number of virtual users or the number of sessions. So this is a feature supported in HammerDB called event-driven scaling that we'll look at later. This allows us to create thousands of sessions. You're going to handle that thousands of sessions, you're going to need some middleware. So if we're testing Postgres, for example, you would need, say, PG Bouncer as the middleware, because then the middleware would connect hundreds of sessions back to your database, and the thousands of sessions would connect to the middleware. And then clearly you understand you're going to need much larger disk requirements in terms of the data area, networking requirements. So we'll place more emphasis on the disk read and write type of the workload. So that's going to take you a lot more time, a lot more expertise, to set up. And ultimately, if you reach a perfectly scaled configuration, high performance I/O, what you will probably find, as we've found over time, that you'll see the same proportion between systems running a perfectly scaled workload as a cached workload. So essentially, that cached workload allows you to get to the same point in time, but much quicker. Okay, so it's a more cut down sort of workload, but it's a faster way to get the same sort of insights, which is exactly what most people are looking to do. So let's move on now. So we've given the introduction of why HammerDB is a better way to run our workloads. So let's have a look at some of the configuration and see some examples of what we can do in terms of running tests using MySQL and Postgres as an example. So one of the first things that I'll highlight, probably the most common error that we see in external benchmarks in terms of the CPU setup, is by default, so when you're running on Linux, by default, a number of the Linux releases default the CPU to power save mode. I'll talk about performance profiles later on, because what we have on the right is a performance profile, but hopefully what you should see, this is a comparison between the default power save mode and the performance mode for the CPUs of a benchmark on Postgres. So you don't actually notice too much of a difference at the outset, but when we're looking at peak performance, we're losing about a third of the performance because the CPU is doing exactly what the operating system has told us, and to save power as opposed to focusing on performance. So what you want to do on any Linux system, if you haven't set the CPUs into performance mode, this is the first step that you should take in part of the configuration. So if you look in the example there, it says in CPU free utils, if you set the governor to performance, then restart CPU free utils, then that will keep the performance governor enabled, over system reboots. There's a tool called CPU Power. You can run frequency info. You should make sure that the driver is the correct one for the CPUs that you're using. So if you're on an Intel-based system, we're always looking to make sure that that driver is Intel P-State, because that's going to allow us to go into that turbo boost range, so to be able to dynamically adjust the frequency for the best performance. And if we look in the frequency info, we should see that it says that the governor performance is being used, and it's going to give us that overall level of performance, and then that boost state, that turbo boost state, to move into those higher frequency ranges is supported. So that's a key thing in terms of the CPU setup that I would highlight at the outset, because it's such a common area that people miss because they install the default and don't tend to make these settings. On the memory side, we've mentioned the cached workload. So for the default cached workload, the key thing you can do, regardless of the database that you're running, is to make sure that the buffer pool and the cache is going to be large enough, to cache the whole of the TPC-C schema. So what we want to see after the ramp up time, when we reach a steady state in terms of performance, is we want to see that most of the data area pretty quiet and most of that data in cache, so that when placing the emphasis on the CPU and the memory. If you can, we recommend using huge pages, in particular for Postgres, for MySQL as well. But, if you can, certainly on Postgres, this will give you additional performance gains. And if you have 1 GB huge pages as well, this will give you more performance benefit than the 2 meg huge pages. Not by huge amounts, but it all gives you additional performance just for a memory configuration. So the key parameters for MySQL and MariaDB on InnoDB is going to be that InnoDB buffer pool size, and on Postgres is going to be the shared buffers parameter. So if there's one parameter that you look at for setting up, the memory for running HammerDB workloads, then this is going to be the key thing to make sure you have enough memory to be able to cache the data. On the disk side, we mentioned before that for the I/O, we're going to focus on the WAL and the redo performance, because as we've just seen, most of the data is going to be cached in memory. So that the key thing really here is to use the highest performance SSDs that you can get for the WAL and the redo. So the focus is not going to be so much on the disk's bandwidth. The focus is very much going to be on low latency. So low latency disk devices such as the Intel Optane SSDs is going to give you really high throughput to that WAL and redo. So you're not going to be waiting on the commits to the log disk, where essentially your session is going to be stalled, waiting for commits, those synchronous commits back to the disk, then preventing you getting the maximum area of throughput. This is a very, very common, in fact, this is probably the most common wait event that we get asked about. So if you're not seeing high levels of performance, looking into the WAL and redo performance is going to be a crucial area for you. When you're setting up the disk, make sure that the partitions are correctly aligned. So take some time just to make sure that you have that correct alignment, using the right tools to do so. Typically, in the example, we use 1 GB redo logs on MySQL and also 1 GB WAL segment size on Postgres. So there's some examples there. So for MySQL, you put the log file size in the parameters, and on Postgres, you're going to set that up on the database initialization. So it's going to be initdb on the WAL seg size. One area I'd suggest looking at is focusing on the components you're testing. If you want to compare the CPUs, in a production environment, of course, you're always going to have synchronous commit enabled. So you always want to make sure the data is on disk before then the session continues with the next step. However, if you're looking at focusing on the CPU components and comparing them, and you're in a test environment running a HammerDB workload, then consider the gains that you might see if you turn synchronous commit off. Of course, we're running very much in a test environment doing that, but if we're looking at testing other components apart from the I/O, then this is something that is valid in terms of seeing the levels of performance that you can get. Of course, to reiterate, in a production environment, you want to make sure synchronous commit is enabled. So for MySQL, it's the flush log at transaction commit, And for Postgres, it's the synchronous commit, parameter. Ultimately, it's up to you exactly how you run the individual tests. Depending on the test scenario, you have the choice of what to do. There's no valid or invalid way of setting the parameters, because it's your own test environment. Finally, on the setup side, a common question is on setting up the client library. So HammerDB, we've mentioned those interfaces in C. They need the C-level libraries from the database that you want to test to load those in dynamically. So within the HammerDB command line, there's a library check command. So if you run that, it will show success, hopefully, if your libraries are available. If not, HammerDB needs to find the path that it's running in. On Windows, it's the path environment variable. On Linux, the LD library path environment variable. You can also, if you go onto the HammerDB lib directory and into the directory for your particular client, you can use the LDD command on the HammerDB library interface to see exactly what client that it's looking for. So as we can see in that example, we want the MySQL client for version 21 for both MySQL and MariaDB, and the example libpq for Postgres. So it should be fairly straightforward. It's a common area that sometimes people find it difficult to make sure they've loaded the right clients, but once you use the methodology, it should be fairly straightforward. Okay, let's have a look at actually running some of the HammerDB workloads now. So we'll just run through a few examples using both the GUI and the command line. I would suggest if you're just starting out, the code underneath is exactly the same between the GUI and the command line. For getting used to how HammerDB works in that multi-threaded environment, I think it's always useful to just start with the GUI if you're just running on a laptop doing some tests, and then you can get used to the overall methodology and approach, and that will make using the command line easier. So if we have a look at the schema build here, if we drill down through the menu, and this example for Postgres, you open up schema build, and then you can see the options parameter within there. They vary depending on the different choices for different databases. So for example, MySQL has storage engines. Postgres gives you the example using stored procedures or functions. And both, as an example, have you the option to be able to partition your tables as the schemas get larger. And one of the key factors in here is going to be the overall, the build performance. So depending on the cores you have in the client and the overall IO throughput actually on the database side. If we look at the schema build choices, what the schema build does, so if you imagine you have, at the moment you have an empty database, or if the database hasn't been created yet, what HammerDB will do is it will create the database, create the table, load all the data into the tables, create the indexes, functions, statistics. So then you have a fully ready schema for testing. So this is the first step to take. So you don't need, unless you want to, I'll talk about it later, you don't need any intermediate flat files. HammerDB will connect to your database, create the data, and insert it all dynamically. This is all for ease of use. This is from learnings in the past of trying to set up test environments, with flat files, manual process. This is a way you can press one button and just create your test schema automatically for you. It's key to note that inherited, it's derived from TPC-C, so inherited from that workload. It's scalable on the number of warehouses. So depending on the warehouses you choose, as you can see from the diagram, that will scale up most of the tables within the schema to different sizes. So this means you can test anything from smaller schemas on laptops right up to the largest 8, 16, 32 socket servers. It creates for you the stored procedures, as we mentioned earlier. So there's 5 stored procedures to run the workloads. And it's virtual users, so threads that create and load that data in parallel. So we are depending on the database performance on how long it will actually take us to be able to do that side of the load. So how many warehouses do you want to create? This is a really common question that we get in terms of, I want to run a HammerDB workload. Then a real common error is, well, I will create, hundreds, many hundreds or thousands of warehouses, and that means I will get much better performance. And this is where it helps understanding, parts of the TPC-C specification, and also, the approach that HammerDB takes in terms of those cached and scaled workloads. So assuming if you're running, the default, cached workload, what a virtual user will do, it will select what's termed a home warehouse at random. Now, 90% of the workload is going to run on this home warehouse. So it should be clear, in this example, we've got two virtual users. The first one selected warehouse 3, the second one selected warehouse 7 from 10 warehouses. So they're going to be mostly hot. 90% of the workload is going to take place on that subset of the data, whereas the other warehouses are going to be, mostly idle. Some of the workload will be satisfied from them, but not a great deal. So we're going to have this concept of hot and cold data. And this is true for these two virtual users, whether we have just say 10 warehouses, 1,000 warehouses, or 10,000 warehouses. We should see a similar level of load right across the schema, because we have this concept of hot and cold data. So you should be able to see straight away that creating many thousands of warehouses, for the same subset of virtual users is not going to give us overall improvements in performance. So you want to avoid this over provisioning, because this isn't the right approach. Instead, because we're selecting a warehouse at random, typically what you want to do is base the estimate on the number of virtual users that you're going to create, and then create enough data to ensure we're not going to have too many virtual users all connecting into the same warehouse. So in this example with 10 warehouses, we wouldn't want to create 100 virtual users, because many of them will then clash on the same warehouse and create more contention than by default that we should see. So typically round about 4x, the number of warehouses as the maximum number of virtual users we would expect is roughly a good rule of thumb to ensure an even spread of the virtual users across all of the data. As an example, on a modern 2-socket system, we typically create about 1,000 warehouses. Now, depending on the system, on a modern, up-to-date, sort of 2-socket, such as the Xeon scalable servers, for us, 1,000 warehouses takes 8 to 9 minutes to load. But this will depend on the number of, on the CPUs, the cores, the disks, the virtual users, and so on. Also, if you're loading across a high latency network, then that's going to have an impact as well, because we're creating data and loading it. There's some limits there within the GUI, and also the data gen feature, which allows us to create flat files, we'll mention in a moment, but there's no actual limit. There's no hard-coded limit to the schema build. So advanced users can go in there, change it, and create as many warehouses as they want. So if we're running the build, so once we've created the options, go ahead and click build, and it will run multi-threaded, multiple virtual users, and we'll see it, creating the schema, then doing, the indexes, statistics, until we finally get that schema complete message. On the command line, it's very similar. The di set command allows you to set the options, exactly the same options that you've seen in the GUI, except you're running it, just setting it at the command line here, and the build schema command runs exactly the same as the build. So the example there shows us, again, it's multi-threaded within the CLI, so multiple threads will then load, so you'll see a lot of messages, and then within the same sort of time, then we will see the same schema is created. And it's exactly the same in the GUI or the command line. So you could create a schema in the GUI and then run tests in the command line, or vice versa. Just as we mentioned before, yeah, especially if you're expecting to see high levels of network overhead, or you want to run some scale workloads with very, very large schema counts, or even if in particular you want to run multiple tests against the same data set, there's a data gen feature which does exactly the same as the build, except just creates the data and puts it into flat files for you. So then you can take the flat files and do a bulk load. So now we have the schema created. Let's have a look at what we want to do to be able to run a test. So there's a couple of driver script options. So what we see, the concept, we have a script editor. So we select some options that will change what we get slightly within a driver script. That then gets loaded into the virtual users, which, as we saw from the concept stage, will all run completely independently in parallel and test the database for us. There's a test script, what's called a test script, which is a very simple run. You should just use this with a small number of virtual users. It will print the output to the screen. So this is just really to verify that the schema build has worked and your system configuration will accept and everything will connect. You start to see some output. This is just to give you a view of what's being returned from the database. But the test script approach isn't what you should be using for running your actual measured test. Instead, what we want is a time script, which gives us this measured test. This allows us a small to a larger number of virtual users and suppresses the output back to the GUI. So we're going to be measuring the maximum levels of performance. If we look in the driver script options, so this is an example from the GUI, you could do the same with the command line. We can choose, in this example, we chose the time driver script. The number of total transactions, you can set this to a very large number if you just want to run through a timed sequence and then have the output at the end. So there's no upper limit really to the total transactions per virtual user. And if you're running for a long time, you'll probably want to set this parameter to a higher value. There's a ramp up time, which is the time for the data to load into the buffer cache, as we've seen for the cache workloads, and then a test duration time, which will be a timed period over which we run the test. You can see some other options there. They're advanced options that we'll talk about in a moment. So once we've chosen and created the driver script and that is loaded, then we want to move down to the next option, which is the virtual users. So within the virtual user options, we can define the number of virtual users, choose to show the output, which by default for a time test we do. And then we want to click create. And as we see in the GUI, that will create a number of operating system threads. And we can see those virtual users, they will sit idle waiting us for start running the test. It's exactly the same in the command line. So at this point, we'll have created the virtual users, but nothing will actually be running yet. So they'll be waiting for the command to start to run the tests. When we start to click run to start, this is where we will log on to the database with the options we've given, and you can start to see we're starting to process transactions. It's not going to print those out. The main reason is actually because in a GUI environment, the actual GUI display will be single threaded. So that means the output needs to be passed back to the main GUI thread to be able to display them on the correct window. So to get the maximum performance in that parallelism, we don't want to restrict the concurrency. That's why we're suppressing the output when we're using these time tests. We start to run this transaction, so the mix of the stored procedures we're running, and so there is mostly the new orders, 45%, and we have other transactions within the mix, which is going to put different emphasis on different aspects of the database workload. So inserts, updates, long-running queries, deletes, everything running at the same time to have a truly testing database workload based on that TPC-C schema. We can see the status of the virtual users, whether they're running. If they error, they'll show a red cross. And hopefully, if there's no errors, we'll get a green tick at the end. If you want to stop the workload, press stop, and that sends a message to the virtual users to stop running. So if we're running a test, with the command lines, with the GUI, with the command line, you have a similar sort of approach. You can, select the various options that you have, exactly the same as the GUI. Then we'll create the virtual users. So within, we see VU set, defining them virtual users, VU create. Again, it's doing exactly the same as the GUI is underneath. VU run is the same as it's running from pressing the run option. And then the timer keeps the main thread essentially busy. For the timer waits for the test to complete. And you can see it running exactly the same sort of outputs on the command line as well. So you have that option with both the command line and the GUI to run exactly the same workload. So while it's running, there's also a transaction counter, and you have the option, if you choose now, to output the values from the transaction counter, so you can see how steady your workload is. If this is an example just from a simple test with MySQL on a laptop, so relatively lower number of virtual users. But what we can see there is the example from the transaction counter where we've dragged the window, so you can drag the transaction counter out of the window to view it separately, and then we get the value at the end of the test result. In this example, 4,351 NoPM and 13,299 TPM, and we'll explain what that is at the moment. And you get exactly the same output within the command line as well. So what does the two? So firstly, a question might be, we've seen these two values of NoPM and TPM. So what does that mean? Which one should I use? It's a relatively straightforward concept, and the best approach is to think of it in terms of the performance dials that you would see on a car, where you have both the speed gauge and also the rev counter. So the speed gauge is how fast you're going. The rev counter is how hard your engine is working to be able to give you that level of throughput. And with HammerDB, it's exactly the same. So NoPM stands for the new orders per minute. So what we're looking at in terms of that transaction mix is just the new orders per minute, while it's also running all of the other stored procedures as well. Not surprisingly, that's a close relation to the official TPM-C, but because it's a derived workload, it's not actually TPM-C, so we call it NoPM for new orders per minute. So that is essentially how fast that you're going can be compared across all of the databases, because you're measuring what's based on that specification. Now, the TPM value, this is very much an engineering metric. So this is how hard your engine is working to deliver that NoPM. And some of the databases have a different relation between TPM and NoPM from each other, because, for example, some support bulk-based operations, whereas others don't. So the direct TPM to NoPM ratio is not the same between all of the databases. However, TPM is particularly useful as that engineering metric, so essentially seeing the user commits and the user rollbacks that can be used to look at all of the other metrics when you're doing performance analysis within the database. So that's why we show, just as you would in a car, essentially these two dials. The key metric is NoPM, but from an engineering point of view, TPM is a really important metric to be able to drill down and see other aspects of database performance. Now, of course, you can automate the workload. So when you want to run tests, we've seen an example of one test there. What you want to do is really run an unattended sequence. So you can define a sequence of tests by increasing the virtual user count and log the output. So you can essentially press go, run a whole sequence, just leave the system, for example, overnight, and then come back and collect the data later on. On the GUI side, there's a feature called autopilot. And on the command line, as you can see, it's very, very easy to script exactly the same functionality. And then you can just leave it running, set a loop, and create a large amount of data. You want to log the output and then collect all of the output later on. The reason we want to do this is you want to create something called a performance profile. So you want to be able to run multiple tests with an increasing virtual user load and measure how the system copes over that load. So this example is with a 56 core based system, and this is typical of the sort of workload that you will see for the cached type approach. So we're seeing near sort of linear scalability as we're ramping up to that actual core count. Then what we'll see is, almost a performance plateau within that middle sort of yellow area. This is where we're starting to reach, the levels of maximum performance, and this is where we'll start to see as sort of the highest levels CPU utilization. Now, if we push, and this varies across databases, this is an example from MySQL. If we start to push the number of virtual users up and start to increase the load, then what we'll see is increasing response times, and then we'll start to see flat to even lower levels of performance. So quite clearly, your approach isn't we'll create such a large number of virtual users and warehouses and start running high levels of load. You want to be aware of where you're going to start to see the maximum level of performance. In reality, what you want to be doing for a production workload is always to make sure you're on the left within that green zone where you're seeing predictable levels of performance. Because once you're in that yellow zone, you're going to be starting to be approaching the points of contention. So you always want to make sure you have enough capacity for the load that you're expecting to run. If we take an example of different systems as well, this is the best way to be able to compare overall between different systems by comparing their performance profiles. So if we look at the ramp up, these are systems 1 to 4 have different CPU counts as well. So it's not necessarily predictable on the number of CPUs, the level of performance that you're going to get. Now, at the outset within the first area, we can see there's not a huge amount of difference. But then as we're starting to move into more the peak performance zone, what you can see is that systems 1 and 3 manage to sustain peak performance for a much, much longer amount of time than systems 2 and 4. So systems 2 and 4 start to move a lot quicker into this over-committed, over-provisioned area, seeing much larger drop-offs in performance. So once you've compared these performance profiles, that would then feed back into your capacity planning for how much load that you would put onto these different systems, because systems 1 and 3 will be able to take a much higher level of load without seeing this drop-off than, for example, the other systems 2 and 4 would. So this really leads into different levels of capacity, and you don't see this from just measuring a single performance point. So hopefully by now you should have a background on building the schema, on running tests, and then doing your autopilot or scripting to compare performance profiles. So once you've reached this sort of good grounding area, you then should be in a position to move on to advanced testing. And there's a number of features here for advanced testing. So we're moving beyond these sort of cached workloads, looking at different areas of the system, probing different areas that we want to test. So the first one of these we're going to look at is called use all warehouses, which allows us to increase the physical I/O. So first of all, the difference, as we mentioned before, with the cache-based workloads, we're only seeing say the virtual users are connecting and using 90% of the workload on one of the warehouses. Use all warehouses, as the graphic shows us, allows individual virtual users to then connect to a larger number of warehouses, which they then select at random from. So essentially what this will do is will increase, if you have a larger schema, it will increase the amount of I/O that you're driving across the entire database. Another feature, if you're running clusters, especially if you have the concept of primary and secondary, what we're doing with multiple endpoints, maybe read write and read only, what connect pooling does is it gives you much more control over the connection. So you have an XML configuration, you can define multiple connections to those nodes and then define a policy of how the individual store procedures then connect across the different nodes. So by default, you could define a number of nodes and then connect round robin, through to them. Or you could, for example, say, I just want to put the read-write transactions on the primary node and then set the read-only to the secondary node. So there's a lot of transaction mix that you can do there, using this connect pooling right across the clusters. It also, depending, some cluster environments will be able to give you the overall performance right across the cluster. Others might not necessarily have the concept if you have primary and secondary. So this functionality also gives you the client side of the transactions. So it gives you a detailed view of the transactions across all the individual nodes. As we mentioned earlier, between cached and scaled workloads, event-driven scaling, this uses coroutines. So what we will do is for each individual virtual user, which is an operating system thread, we allow that virtual user to then manage a large number of sessions using coroutines to give us this fixed throughput by running the keying and thinking time, which is the delay between the individual transactions asynchronously. So essentially, one virtual user will be managing a large number of sessions, so we can go from hundreds, which are maximizing the system utilization, to many thousands. It's worth looking at the TPC-C specification, sort of understand the size of the database you need. Also, as we noted earlier, you're going to need middleware. You're going to need to increase the I/O and the networking, and expect to see around about 1 new order per minute per session. So example, if we have 1,000 warehouses and we're connecting 10 virtual users to each warehouse, expect that level of configuration to give us around about 10,000 new orders per minute. So you're really going to want to think about how you scale up the system if you're taking this approach. But this allows us to do almost the official type approach of a scaled workload compared to that default cached workload. As you would expect, there's also an option for time profiling. So we have two packages called xtprof and etprof. So that's the xtprof allows us to profile all of the virtual users and outputs the output to a separate log profile, whereas etprof just runs on the first active virtual user, but then gives us the output every 10 seconds. So there's an option there to be able to view the latency, which is also very important across all the virtual users for all of the transactions. Finally, for the advanced features, we have variable and step workloads. So clearly, you're not going to run this and capture the overall levels of performance, but this works very much with the time profiling. So you can vary the difference, look at the difference between response times. This is almost where you're looking for errors and trying to work out when you're moving into that over provisioned zone by increasing the load up to a certain point, to where it's overloaded. This uses the primary replica feature where we have multiple instances of HammerDB. This runs only in the command line, this particular feature, but allows multiple replica instances to connect back into the HammerDB primary instance and then get triggered over time. So we're starting to increase the load and we can see variations up and down in performance. So if we want to monitor performance, there's features such as the CPU and database metrics. This is built into HammerDB. What we want to see is the CPU, performance. So in this example, the CPU average, is it 50% of all cores or a 50% of the cores at 100% and the other 50 at 0? So the CPU metrics allows us to get this visualization and detect if there's any sort of imbalance across the system. In particular, look for interrupts. Are some cores maxed out and we're seeing red just on some cores for system time because they're handling all of the system interrupts. Over time as well, HammerDB supports database metrics for graphical metrics for other databases, and sort of similar to the graphic we see here, this is in progress for Postgres for the active session history. For some external tools, if we're looking at MySQL, then InnoTop, is a good tool that can give you an example of, exactly what commands are running on the system, and what they're all doing. So especially some of the statements that have the emphasis on locking. If we look at, Postgres as well, pgstat statements as well as pgsentinel can give us, an overall view. And if you have a high performance system, usually it tends to be the commit log where we see sort of the highest level of wait events. But this is very useful for getting that overall view. And this is what should end up in the graphical, features, that we see later on. Another tool I'd recommend, an external tool, is called Linux KI from HP. And this example, comes from what we saw earlier. So when we said that Sysbench runs, 20% of the time within sort of the round trip, we can see here using Linux KI, that makes it clear. So we can see on the HammerDB side, we're doing a lot more locking on the system side, whereas within the top events on the Sysbench side, we're seeing a lot of receive from and send to on the socket networking. So Linux KI is a very good tool for going down beyond the database statistics and looking more at the operating system level to see if we have contention on areas, see if we've got an even spread across the CPUs and contention on those areas that we mentioned, such as interrupts. Okay, just to wrap up, we've sort of seen a lot on the transactional side. HammerDB, as we mentioned, also covers analytics, which is a completely separate, similar length time presentation. It's more complex. It covers all, it's derived from the TPC-H schema. This is looking at column stores and parallel queries, and there's also separate workloads called cloud queries as well. So this is very much looking at your complex parallel query type workloads traditionally. As the next steps, if you're looking to run some of your own HammerDB tests, the first step I'd say is go to the website, have a look under the benchmarks tab, and see, is there something that somebody else has already done? If they already run some workloads that you can use. And if you're running your own tests, think about how you can publish your findings for other people to use, because that's how community works. It's about making the performance open source to give everyone the benefit so we can improve database performance and workloads overall. Coming soon, we're at version 4.1, already. We already have the pull request. So thanks very much to Hua for pull request to add MariaDB as a separate database. You can run against MariaDB now, but you need the MySQL client. So coming in the next release, we'll have MariaDB as a completely separate database, which gives us the opportunity to diversify the workload from what we're running with MySQL and have contributions to each. So we can have different enhancements across those different databases as they both diversify over time. If you want to contribute to HammerDB, we've mentioned it a lot, it's open source, it's on GitHub. You can review all of the code, all of the documentation is open source. If you want to add to that as well, it's in docbook format. If you don't want to get started, committing code at the moment or writing, putting pull requests in, there's issues. You can read, new features, for example, or go to the discussions tab, to ask questions. And this is also where you can get direct access to the binary releases. But it's very much community driven, so you can get involved and make database testing as best possible as it can be. So thank you very much. I hope you've learned enough about HammerDB, and at this point, I'll see if there's any questions. Thank you.